a really important thing, and I think you people might like it better than my other students because as programmers, you're probably not terribly afraid of math. And this is a mathematical concept. My other students are generally terrified of math and do not like to think in mathematical logic. As you probably know, most Americans in 4th grade are exposed to terrible training in algebra, and after that they decide math is horrible and never look at it again. So the point here is, well, this is the wrong purpose. Anyway, the point here is, consider what you have to do if you're going to make a machine learning algorithm. Think about like a Tesla car. It's got a camera taking a live video of what's in front of the car. It may be 4K by 4K resolution, so you've got millions of bytes of data coming in many times per second. There's no way you can possibly process all that data in any reasonable amount of time to determine, am I about to hit somebody? The same thing's true of your visual system. Your eye sees a lot of pixels worth of data, and yet you can do processing incredibly fast. If someone throws a baseball at your head jerks out of the way within 50 milliseconds. So somehow, with all that data, you're able to quickly zero in on what part of this is important. There's something getting big fast coming at me, and calculate that it's actually going to hit you very fast in about 3 stages of calculation. So this is the fundamental problem. Now, if you consider, let me just draw a little picture here. But if I have a curve curving across this page and I'm going to have just samples, then I would, if I wanted to trace out the shape of a curve, I'd want to have a few samples tracing it out. And you ask, how many samples would it take? If I was going to have a curve that, say, goes up and down, and I'm only measuring discrete samples, then how many samples does it take to shape out the shape of this curve? And you would figure you might need, say, at least 10 samples evenly spaced across this field to trace out the shape of the curve. But if all your samples were crowded in at the edges, you would never learn the shape of the curve. If all I had was a bunch of measurements over here, and then none of this, and just a few measurements at that edge, I have no idea what the shape is in the middle. And this is essentially what I was saying before. You have a problem that the input data has too many dimensions and you have to lower it. So you can first start by just doing it abstractly. Here, we're going to take hypercubes and we're going to find out how many points are near an edge. Now, if you have a one-dimensional hypercube, a number line from 0 to 1, and you choose random points, they'll just be randomly distributed like this. Most of them will be in the middle, only a few will be on the edge. If you have a square cube, some of them will be on the edges, top and bottom, and right and left, but most of them will be in the middle. But the problem is, think about this, if you have like 100 dimensions, then you're choosing 100 random coordinates. And there's a very high chance that out of those 100 coordinates, one of them is very small, like less than 0.01. So it is on one of the edges. As the dimensionality goes up, the amount of edges compared to the center goes up and up and up. So if you run this, this will just put 1,000 random points in hypercubes of various dimensionality, and then count how many of them are within 1% of an edge. So that's all it does. And so you get a chart here as soon as it's done allocating me a virtual machine or a container to run in. All right, so in 2 dimensions, only 25 out of 1,000 points are on the edge. And 3 dimensions, that's fine. But by the time you're in 100 dimensions, more than half of the points are on an edge. And by the time you're in 1,000 dimensions, all the points are on an edge, and all higher dimensions. And 1,000 dimensions is nothing. That's a 30 by 30 pixel image. You couldn't see anything with vision like that. And Teslas and humans have much better vision than that. So you have a lot more data coming in. And what that means is statistically, you can't possibly have enough data to trace the actual behavior of the real world thing you're measuring, because your data is all on the edges. And you don't have any clue about what happens in the middle. So you cannot make a model of the world that reflects the complete richness of the data coming in. What you must do is reduce the dimensionality. And in your brain, this is done by the amygdala, I think, the special formation in your brain, just to discard almost all the information that comes in your senses, to figure out that most of it is not interesting and throw it away, and pick what part of it is important and pay attention to only that. And machine learning has to do the same thing. And here's another similar way to do this. You can just make high dimensional cubes, put it in random points, and then figure out how far apart the points are. Because if your cube goes from 0 to 1, then you really need like 10 points. You need points like every 0.1 or something to trace out the shape of what's going on in there. And so you might ask, how far apart are the points? This just makes random points, 2 random points, and then calculates the distance between them. And here's the average distance between points. So here, you have 0.5, but by the time you get to 1,000 dimensions, they're 12 apart. And remember, the cube is only 1 on a side. So being 12 apart is a big distance, and here they're 100 apart at 100,000 dimensions. So again, you can't possibly ever have enough measurements to really trace the richness of anything with that many number of dimensions. But of course, you don't want to. If you think about your visual system, I don't want to predict every speck of light where it's going, like a cloud of mosquitoes. All I want to know is a rock coming at my head. That's just a few bits of data I really want. I want to find the good stuff in that haze of vast amounts of information, most of which doesn't matter. And there are ways to do that. So this is called principal component analysis. So let's take a data set that we have used before, which is these numbers that are handwritten, and you're going to try to label them at the correct label. So let me go to this thing, and I'll clean off these old ones and put in a new one. All right. Shrink the phone a little. And so here it goes. I'm going to import these images and just plot them out so we can see them. I have to kind of slow this going on here. So you'll see that's what the images are going to look like. We've seen these images before. All right. Now, the question is, these images are currently 28 by 28 pixels of grayscale. So that's like 712 dimensions. And you probably don't need all 712 dimensions. Your brain certainly doesn't process it. I process this line as just one line, and this is pretty much the same, and that is pretty much the same. I don't worry about the fact that there's probably 300 pixels different between that and that, and that and that. I just boil it down to, well, there's one vertical line. That's all I need to know. And so we want to do that. So we're going to choose the right number of dimensions. So here we have images, just so you can see what they look like. And now we're going to do principal component analysis, which is quite simple. What you do is you take all the data and you just plot it in a high dimensional space. And then you try to find a plane that captures most of the variation. So if the data is scattered, like this data I made here, this data is in 2 dimensions right now, X and Y. But you can see if I made a tilted line here, I would catch most of the actual meaning of that data with 1 dimension, just by having a diagonal line here. That's the point. The original data has a lot of dimensions, but you can probably draw a plane and project it onto a plane, and if you choose a good plane, you will capture most of the actual information in that data with fewer dimensions. That's called principal component analysis. And you do it here. As you see, as like everything in Python, I just import a library to do it for me, PCA. Then I run PCA on this thing, and I say, find the number of dimensions that will capture 95% of the variance. So all it does is follow the shape of those dots in high dimensional space until there's only 5% of variance that is not captured by them. The original data was 784 dimensions, but I only need 154 dimensions to capture 95% of the variance. So that's one way to decrease the dimensionality of a problem. All right, and now you can use a random forest like we did last time, machine learning, and you can run your random forest on the, we're going to use 100 training images and only 10 iterations. And what this is going to do is first reduce the dimensionality with principal component analysis, and then do a fit on what's left. So it will learn. So let's see what it chooses as the best fit it can do with that model and that restricted set of data. So here's the principal component analysis, and here's the fit of this data, just taking it to 10 steps to train it. And a little slower than I like, but anyway. Oh, there we are. So it's down doing a random search. Now it's doing the training. This little green triangle tells you which thing it's on. So it's training the model, and then it's going to predict and print the percentage that was correct. So I won't wait for it. It's being a little slow. The answer is here. The answer is, with 465 estimators and only 23 dimensions, it can get 85% accuracy. So remember, it took something like 120 to capture 95% of the variance. It lowered it all the way to just 23 dimensions out of the 784, which is really a lot of reduction. And now we can see what that did. You can plot out the results of keeping only the components that were used by this model. All right, it's still doing the fit. That's annoying. I'll start this running so you can look at it live. But I'll just go to the example. Here's the example. Here's the original, and here's when you only keep the 23 most important components. So as you can see, it's doing quite a lot of distortion of the images, but most of them are still pretty easily visible to the human eye. That's a 7, that's a 9, that's a 4, although it's starting to look kind of like an 8. So, this is, that's how you actually reduce variance, reduce dimensionality, and I say your brain does it too. You absolutely have to do this. Your senses pick up too much data, and you have to find some way to throw most of it away. I know flies have been completely reverse engineered because they have very simple brains, and flies have only 5 things they can see. They can see when something in front of them is getting bigger fast, they're about to land on something, so they put out their feet and start tasting it to see if it's food. When something behind them is getting bigger fast, they're about to get squashed, so they jump and fly randomly. When there's a small dot of dark in a light field, that's a mate. They chase the mate. They have a whole algorithm and chase it very efficiently through the air. And if they fly for more than a few seconds without anything happening like this, then they randomly tumble to choose a new direction. And that's about it. That's all they do. Ants also have a very simple algorithm. And this thing of having warm blood and intelligence was just not worth the bother. They can live on almost no food by not bothering to have warm blood or intelligence. And they were here before us, and they'll be here after us. They have a very successful way to stay alive. And, that's an example of how you throw away most of the data. They got a lot of sensors in their eyes like we do, but they boil it down to just a few signals that are important to them and ignore all the rest. And so do we. All right. Anyway, let me check for comments in the Twitch. There are none. All right, I'm going to stop this video.